Hello, and welcome to this section 5.2, the definite integral. In this section, we're going to define the integral, the definite integral, and tie it to what we did in section 5.1, where we approximated areas under curves. So again, we're going to be using the same things we used before. We didn't really use these summation formulas much before. We'll use them a little bit now in this section. And then using limits at infinity. So let's start with the definition of the definite integral. So it's denoted like this. This is read the integral from a to b of f of x dx, and this is the integration symbol. And it's a variation of an s for sum because it's based on those sums that we looked at in section 5.1. which are Riemann sums. So if a function f defined on some closed interval ab, if I divide it into n intervals, like I did in section 5.1, and then in each of these intervals I take some point, some sample value in each interval, then I'm going to define this definite integral as the limit as n goes to infinity of that function evaluated at one of these points from each interval times the width of each interval, which is delta x. So delta x is the same thing we saw before, where we took the length of the interval, which is b minus a, and divided it by n. So this we've seen before, but now what we're doing is adding this limit as n goes to infinity. So last section we saw that these sums were approximations of areas under a curve that's above the x-axis. Now when we add this limit as n goes to infinity, we're taking smaller and smaller intervals and more of them. And so that limit is the definite integral if this limit exists. So there are a couple of notation things I want to show you. So this little squiggly above x sub k means that I can pick any value from each of these subintervals. It doesn't have to be the right endpoint or the left endpoint or the midpoint, because these intervals are getting smaller and smaller and smaller. Those x values can change as n goes to infinity. In the text, instead of using this little squiggly, they use an asterisk for a sample value, but I'm using Desmos for these slides, and when you type in an asterisk, it turns it into a multiplication. So anyway, f of x itself, back into the definite integral, the function itself is called the integrand. And dx just indicates that we're integrating with respect to x, and that we'll talk more about that later in the course. But that's analogous to delta x. And then a and b are called the limits of integration. A is the lower limit, and b is the upper limit. So here's a few things you want to know about the definite integral. It's just a number. That looks rather intimidating. But remember, a limit, if it exists, a limit just evaluates to a number. So you're going to be getting just a finite value here. And that Riemann sum that we're taking the limit, that summation that we're taking the limit of, is called a Riemann sum. And again, this is just an estimate of the definite integral. Now, if f is positive, meaning all of its values lie above the x-axis, the Riemann sum approximates the area under the graph of f and above the x-axis. And if f of x is positive for all values on AB, then this definite integral is the area under the graph. It's not an estimate. It's the exact value. So that's if f is positive on AB. Now, if some values of f are positive and some are negative on AB, remember f is continuous though, then it's not the area anymore, because an area is always positive, and this might evaluate to something negative. So it's called the net area, which is the area above the x-axis minus the area below the x-axis. So let's talk about net area a little bit. Here's a good example. So I have f of x equals x cubed, and I'm going to look at it from -1 to 1. So the integral from -1, definite integral from -1 to 1 of x cubed dx, I write like this. And its value is actually 0. And the reason is because the area, this is symmetric, the area under the curve, this piece above the x-axis, is equal to this area below the x-axis. So like if I took this and actually flipped it up there, it would be a positive area. So these cancel out. So it makes sense if you think about the definition in terms of Riemann sums. These values, when you think of the Riemann sums, your function values that you're summing up are positive. And here the function values you're summing up are the negative of these function values. So when you sum them up, you're going to get a net area of 0.